Now we're going to look at the convolutional neural network fundamentals. We'll review a couple of key components of neural networks and see why they are designed in this particular way. And at the end of this, we'll do a hands-on workshop as usual, where we'll build our own neural network from scratch completely. We'll outline all the layers in the PyTorch framework, and we'll train it to recognize handwritten digits. But actually, that neural network can also use to recognize all kinds of small-sized images. So before we go into the neural networks, so the design, I want to show you a really cool website. It's called playground.tensorflow.org. And what it does, it simulates a simple neural network in the browser. And first, I want to talk about why people are so interested in deep learning these days and in the last few years. It's definitely the industry is adopting more and more deep learning models every day. Machine learning and statistics, which in some actually fields it was called, it could be called either way, existed for quite some time. And we knew how to build different models for different problems for the past several decades, really. So first, I'm going to show you this. So I'm going to build this simplest neural network with just neuron. If you'll actually look at the math behind this simple neural network, then it will actually correspond to a classical machine learning algorithm called logistic regression. And what logistic regression is good at, and what actually it does, given any two data sets, two types of data points, it will find the line that separates those data sets in the best possible way. So for example, if my data set are these two blobs with two types of data points with different colors, and we want to find a model that separates them so we can make future predictions which part this new point belongs to orange or to blue one, I can use this logistic regression, and now I'm going to run the training. And as you can see, it easily finds this line, right? There's definitely a separating line. We solved this problem. Now we have this model, and it's going to work. If we're going to give an orange point in the future, our model will correctly predict it's an orange point. If we'll give point from the right side, it will say that it's a blue point, and it works. So this is good. But let's say now we have a slightly different problem, and it's actually different, that has a different data set. And this is our data set. So now we have the same idea, two types of points, orange and blue, but now they are separated by basically a circular boundary. So if we simply feed this data into our algorithm and try to train the model, well, nothing good will happen. Purely mathematically, it will try to find a way to stick a line somewhere where it minimizes the error. It's called training loss. But the training loss is still huge, 0.3, 0.4, and it's almost not decreasing anymore. Well, we want this to be very close to 0. So the model fails. And this could be it. We could be done. But actually, there's a solution to this problem that has been used for quite a few years. And that is, we use raw inputs, x1 and x2, in this particular model. But we can actually transform our inputs and pre-process them before we feed them into the model. Specifically, TensorFlow, TensorFlow Playground allows us to pass in squares of the inputs, right? And so if you have a data scientist, or you're a data scientist, and you look at this data set, you will notice that a circle would be a very good separating boundary, and the circle is a quadratic function, essentially. So you might want to try passing also quadratic values, transform the inputs, and then train the regression again. So let's see what happens in this case. And there you have it. So now we got a circle that separates our data sets, data points very nicely, and we can use this model for this problem. So now if we pass the orange dot, our model will correctly predict it's going to be outside, the blue one is inside, and it works again. So again, we can use this model. But as things continue, if we use the third data set, that's like this, and we'll try to run this, apply our model to this data set, it won't work again because it's this different data set. So now we need again to look at it to analyze it manually, because of course the circle or a line cannot really separate this data set, right? It doesn't really fall into one of those two categories. So now we need to analyze again, spend time, and do what's basically called feature engineering. And this can go on forever, right? So every new data set potentially can require us to redesign our model quite a bit, change the features, spend a lot of time looking at the data, plotting the data, making guesses, trying them, see what works and what doesn't. So this takes a lot of time, this is expensive, requires a very knowledgeable and expensive people to do all that. So let's take a look at the neural network, what the neural network will do. And the neural network will do almost a magical thing. With enough layers and enough neurons, so I'm gonna add 3 layers and let's make 6 neurons each. And you can play with these parameters, add a few more, remove a few more, it should not have a huge difference. And now I'm going to remove those quadratic inputs that we added previously. So I'm just gonna feed the raw data, x1 and x2. And let's try all these data sets again. First, the simplest one. All right, well, this seems to be working. Our model found the line. Now let's try the circle. And now we found the circular boundary, which will become probably more round as the training continues. So we can now try this kind of the 2x2 data set. Let's see what this neural network will do. And the neural network will solve this problem. So I found the right boundaries. Actually, there are 2 of them now that separate blue and orange quite nicely. And finally, the most difficult of them all, the spiral. Let's do that. And this will take a bit of time to train because it's a pretty difficult data set. So it will take a while before all the weights will be set in a way that it actually approximates the spiral. But if you keep an eye on this training loss, you will see that it's slowly decreasing, then it might accelerate. After a little bit, it will start to decrease faster. And our model is slowly converging. And if you notice that we applied the same network to 4 different data sets, or 3 already, and the 4th one is in training, and the model has done the right thing with 0 feature engineering, right? We just fed the raw data, the same x1 and x2 in every single time, and the model figured out the right separation boundary, built the model that's actually going to be very predictive and will work. So, and that's the very attractive property of deep learning, is that it requires no feature engineering. You simply throw the data at it, and if you provide the right labels, like in this case, orange and the blue dots, the model will train. Of course, this comes with a couple of costs, because nothing is free. The first cost is, of course, is the computing power. Instead of, if you remember at the beginning, we had a very simple logistic regression that only had 1 neuron, so there were only a couple of computations to be done in that case. This neural network has 6 by 3 by 6, 18 neurons, and each neuron is connected to each neuron before and after. So it's a quadratic number of weights. So here we have already 36 parameters between first and the second layer. And here we have 36 parameters more, and all need to be trained. So this takes a lot of processing power. And the second part, for the same reason that we need to train a lot of parameters, we need a lot of training data. So neural networks are very hungry for data. So we need to throw a lot of training samples at the network and wait, as you can see, for quite a bit of time before it will converge on the model, on the right model. So as you can see, the training loss is still decreasing, and if you'll do it in your browser and you wait long enough, you will discover that this neural network will approximate the spiral and will separate orange from the blue. But these neural networks, as you can see, have huge amount of power that can be used to solve many real-world problems. And that's why they are so attractive and becoming more and more popular. So if you've looked up anything about neural networks in the past, you probably have seen a diagram that looks like this, with circles and lines connected to each other. In fact, we saw something just like that in the previous example in the playground, only instead of circles they had squares. So what this actually means is this is a graphical depiction of a very simple formula that's being calculated, computed by any neural network. And what the formula does, I will show you in this example, is we'll pretend that the numbers on the left are the inputs. It doesn't really matter what they mean, but the numbers we feed into a neural network. And then every neural network has parameters, or they're also known as weights. And the weights work like this. For every input, we have n weights, in this case 4, that correspond to the number of inputs, and possibly one more that serves as the constant. And then we apply the formula where we multiply each weight, here's the formula, each weight by each input, and we sum them up. And this is the output. So we're almost there actually, because if that's all we do and we continue to multiply and sum it up, we're actually not going to do anything super interesting. That will be just so-called linear function, and it can work with the linear objects, but nothing really as powerful as what neural network can do. To add the power to neural networks, we also have a so-called nonlinearity. So there are several types of nonlinear functions, and as the name says, they behave in a very kind of nonlinear way. And one of the most popular functions used today in deep neural networks is called ReLU, or rectified linear unit. And it works in a pretty weird way, although a very, very simple way. This function, if the input is a positive, the function simply outputs it as it is. If its input is negative, it truncates it at 0. So in other words, it truncates any input at 0, and if it's positive, you simply get the number itself. This function is really fast to calculate. It's really good for neural network training, but it gives us all the power that we need. So in this case, the number is negative. We're going to truncate at 0. Let's calculate the next number. So if you will we'll check my math, we should get 11.9. The number is positive, so it stays as is. The next number is minus 0.11. It's a negative number. We're going to truncate at 0. And finally, the positive number stays as is. And this layer is done. Another important part about neural networks is that they work usually with the previous layer, and they only care about the inputs that come from the previous layer. How the previous layer got these numbers, the subsequent layer doesn't really know. So it allows us to build deep, neural networks that still maintain internal simplicity because of this calculation. So now we can go to the next layer, and we only need to now worry about the inputs from the green layer. Again, we're applying the weights. I'm not showing them again for simplicity reasons, but there were some weights. We get the negative number, we truncate at 0. Again, multiply weights by the input, sum them up, positive number, we're done. And that's pretty much all that neural network does on the forward pass. So the training is quite a bit more complicated, and it uses an algorithm called backpropagation, which we're not going to talk about in detail today. But overall, when we do the inference, the neural networks actually carry out very, very simple computation. And the use of nonlinear functions is what allows the neural network to approximate any other function out there. In fact, there is a theoretical proof that shows that a neural network that's big enough can approximate any function. So, and that's what this kind of graph means. Basic operations of multiplication, addition, and applying nonlinear function. And that's what produces the neural network output. So what we're going to do, we're going to build a neural network, pretty simple one, that will take as an input a number, a digit, handwritten digit, and will predict, classify what the number is written on this image. So to us, this looks like 4, of course, but the neural networks work with underlying numbers. So what we're going to pass is we're actually going to pass this square matrix of 28 by 28 pixels, where each pixel will be between 0 and 255, and it will be showing the intensity of that particular pixel. So the white would be 255, the black would be 0, but other than that, we're not going to change anything in the image. We're going to pass it as is, and the neural network will learn on its own to recognize that this array of numbers actually corresponds to number 4. So we can actually take the design that we discussed so far, which is called a fully connected network, where you have a layer of neurons that are connected to the next layer of neurons, and they have quadratic number of connections, and start building this neural network. But it's not quite what we have, and convolutional neural networks differ from a fully connected neural network in a very important way. And to understand why and what the problem is, let's imagine that we now took our fully connected network and simply folded the layers from the linear representation into this square representation that more corresponds to images. But other than that, it's the same idea. Same inputs on the left, middle layer in the middle, and now we want to calculate the new values. So we get the inputs, we have weights, we multiply weights by the inputs, we sum them up, apply nonlinearity, and we have our first output. And then we'll repeat that for the second output, for the third output, and so on. So this is exactly the same calculation that we've done a few slides earlier. It's just represented in a slightly different way to look more like an image instead of the linear long vector of numbers. So now let's imagine that we want to work with images that are 200 by 200 pixels, which is not a huge image, really. So 200 by 200, what's the total number of inputs? The numbers we have to pass into this network. So if you multiply 200 by 200, we'll end up with 40,000 input values. Let's assume that the second layer has the same size. It's also 200 by 200. Then the question is, how many connections or how many weights do we need to map the first layer to the second layer? So let's think about it for a second. So to calculate the first value, or the third value in this case, we need to take every single input value. We need one weight per input. So we're going to have 40,000 weights. We're going to multiply them with 40,000 input values will be multiplied by 40,000 weights. We're going to sum them up, add the nonlinear call, and we're going to get one output. The second output, or the fourth output in this case, will have a new set of 40,000 weights, and so on and so forth. And we have the total of 200 by 200, 40,000 outputs. So the number of connections that we're going to have, the total number of weights that we need for this a fairly simple, just one layer network, is 40,000 by 40,000. So this would be 1.6 billion connections. If you use a float to represent one weight, then this already will be 6.4 gig of RAM just to keep just the weights, nothing else. Usually networks have an overhead, so you're already talking about tens of gigabytes of RAM just for one simple network. And if you only have 10 layers, and as you will see, our networks, modern networks, have a lot more than 10 layers. We're looking at 16 billion weights and basically hundreds of gigabytes of RAM needed to just keep this data structure in memory. Now, this also will require massive computational power, because to just pass the image forward to calculate the one output for one image, we'll need to multiply billions of weights by billions of corresponding inputs, sum them up, and do these additional calculations. So this will be very, very slow and will take a really long time to train this neural network. Even on modern hardware, this will probably take months and years. And that's a problem number one. The problem number two is the same, is that we have so many connections or so many weights, billions of weights that we need to train. That in order to train so many parameters, we also need a lot of training data. Well, there is no hard rule. Usually a rule of thumb is the size of the training set should be in the ballpark in the same order of magnitude as the number of parameters that we want to train. So in this case, if we wanted to train billions of parameters, then we need kind of billions of images, labeled images that we will use the training set. And such data set simply does not exist. And even if it existed, it will take forever to use billions of images to pass through such a massive network to train and to get something usable. And even if you do train this network, you cannot pretty much run it on anything because it requires so much hardware. So all of these practical and theoretical limitations such as requirement of huge amount of data, made these simple, fully connected networks non-workable for computer vision. What helped design neural networks is the research done in the past, and there were a lot of different directions on this research, and I just want to bring up one of them that was done in 1960s by two neuroscientists, by David Hubel and Torsten Wiesel. They set the task to themselves to figure out how a cat's neurons respond to visual stimuli. They connected wires, electrodes, to particular cat neurons, and then they started showing images to the cat and trying to register when the neuron fires. And for the longest time, that didn't work. They tried dots, lines, squares, all kinds of images, and the neurons just wouldn't fire. And so one day they were sleeping, since it was 1960s, they used a real world offline tools, such as a plate of glass with the drawn dot on it, and they were slipping it in the projector to show it to the cat, and suddenly one neuron started firing. And after they spent some time, they finally figured out that the neuron was responding to the edge of the plate of glass, when the edge was getting in the field of view, and it was 45 degrees, and it was moving from left to the right. Only under those conditions, the neuron would fire. It would not fire if the line did not move. It would not fire if it was not a line but some other shape, and it would not fire if you move it from the top to bottom, only diagonally, only from the left to the right, and only when you move it. So, which was quite remarkable, because we know what our neurons look like. We saw them under the microscope, and all the neurons are the same, right? We don't have this massive Frankenstein neuron that recognizes diagonal lines that are moving from the left to the right. So they hypothesized and later proved that visual cortex in cats, and all animals really, is a hierarchical layers of neurons that are kind of the same, but they rely on the outputs of the previous layers. And because of that, subsequent neurons can recognize more and more complex objects. If the first neurons that are very close to our retina can respond to a simple presence or the absence of the signal in a certain part of the visual field, then the neurons that are 3, 4, 5 layers later can recognize exactly what happened in the experiment, which is the moving line from the left to the right. And then the neurons even down this path can recognize a more complex concepts, such as maybe a cat's owner coming in with food, and there would be a neuron that fire, triggering a response that it's a good time to go and get some dinner. So these ideas were borrowed by now computer scientists designing deep neural networks, or just neural networks, and we applied the same idea. Just use layers and layers of these neurons, now artificial neurons, of course, which is a mathematical concept, and hope that when we train neural network correctly, it will do the same thing the cat's visual cortex did. As we go down the path, the neurons will be learning more and more complex concepts about the image, and finally we can shrink this noisy input of random pixels basically into our classes and train as many outputs as we need. So in this case, in this toy neural network, this neuron would be excited or will fire when the image of the car is shown, and this neuron will respond to the giraffe and not the other way around. So the one idea that we took from the neuroscience research is the hierarchical model of this recognition. And the second important idea is that the visual field in the animals, and the cat specifically, is local. So neurons respond only to things that happen next to each other in a small area, and they ignore what happens on the other side of the visual field. This actually solves the computational problem quite efficiently, and that's another concept that we borrowed into for convolutional neural networks, the concept of a convolution. So if you remember from the previous few slides, this is how we calculated outputs between two layers. We take all the inputs, all the weights. In my hypothetical example, there were 40,000 inputs, there were 40,000 weights, and we calculate a single output. In the convolution, what we do, we drop almost all of the weights except for a small number in a certain region. In this case, it's 2 by 2, just for an example. In the real convolutions, it's typically is at least 3 by 3 to up to 7 by 7. But still, it's a very, very small number of weights. 4, 9, maybe 49. So we went from a huge number of weights to just a few dozen at most. And now we're going to calculate the output in exactly the same way as before. Take these weights, multiply them by the input, sum them up, apply the nonlinearity, and we have the first output. And then we're going to use the same weights, just going to slide down by 1 pixel and repeat this calculation. And that's what's going to give us the next cell. And then we'll continue until we'll run out of input. That's it. That's how the convolution works. And the key breakthrough here is that we went from billions of weights, in the previous example was what, 1.6 billion to just 4 weights. In my hypothetical example, realistically it'll be about 50, but basically it's a tiny number compared to the weights that the fully connected network will have. And because of that, convolutional neural networks can be trained. They're very efficient, and they actually work very well because they replicate a general sort of neuroscience discoveries that we found a few decades earlier. Often the filter represented is just a matrix of numbers, and it actually has a graphical applications. So if you use Photoshop or some other graphical software, they would often call filters is exactly what this is. It's a matrix with some numbers, and depending how this matrix is designed, when applied to an image, it will produce interesting modified outputs. So for example, the vertical line, if you have ones and zeros everywhere else, and then you apply it to an image, it will emphasize vertical lines. Horizontal filter will emphasize horizontal lines. And then this information can be used in subsequent layers to do more processing. In reality, of course, when the neural network is being trained, we don't specify these filters manually. In fact, these filters are essentially the weights that the neural network has, and they initially set, like in all neural networks, randomly at first, and then they set to their final values through training. So a neural network figures out by during the training what these weights should be set to help it solve the classification problem. So probably usually if we look inside a neural network, we're not going to see such nice and easy intuitive concepts, but fundamentally the idea is very similar. And so if we go from the fully connected network to a convolutions, then all it really changes is that instead of having all the input cells connected to all the output cells, we just have a small subset of them connected to the output cell, and we're just going to move these connections in this sort of not very intuitive way because it's a two-dimensional image, and when you do it one-dimensional, it will be jumping like this, but otherwise the idea is exactly the same as before. Only much smaller number of weights, which makes the neural network much more efficient. And the second concept that we have in convolutional neural networks is called pooling. So once we've done the first round of processing and we calculate the first intermediate layer using the convolution, we can shrink it now by a factor of 2 in both directions by using different aggregation techniques. And the simplest aggregation technique is actually just picking the max value. So the way pooling works is we have this 2 by 2 filter, 2 by 2 matrix, and it just slides by 2 pixels in each directions and picks the highest value from each quadrant. So the left one, 1, 1, 5, 6 will give us 6, 2, 4, 7, 8 will give us 8, and so on. And this way the image will become half the size. Then we continue applying these layers until the output shrank to basically the small number of output neurons that respond to the highest classification that we need. So for example, if we're doing the digits, then we will just stack in convolution pooling, a couple of the connected layers at the end, because that's where the size of the inputs becomes very small and the fully connected layers now become very manageable and can work. And ultimately we want the output that would be, for digits, it would be something between 0 and 10. And so we'll get a neuron that fires that corresponds to a number that we show. In a more general way, we can pass different types of images. Again, they go through the same types of convolution and pooling and end up in a few handful of classes that we can use. And as we saw earlier in the earlier sections when we did our first demo, we can use the pre-trained network to pass images, and the pre-trained networks that we used had 1,000 classes. So it's a fair number of classes, but the idea is the same. We pass an image that has 40,000 inputs, and a network condenses them into a small number of predictions. So these ideas finally were consolidated and used with great success in 1998 in a neural network called LeNet-5. And Jan LeCun and Yoshua Benjoa and other team members designed this network. And it uses exactly the elements that we've just discussed. So it works on fairly small inputs. Here it says 32 by 32, but modern implementations typically use 28 by 28. We have convolutions. Then we have pooling that shrinks the dimensions a factor of 2, so they become 14 by 14. Then more convolutions, more shrinking, and finally we have a fairly small fully connected layer, only 120 cells and 84 cells, and ultimately produces the output of 10 cells. And each of these neurons, output neurons, corresponds to one of the input. So if we show the number 0, then we want to see the first neuron set to 1 and the rest of them set to zeros, and so on and so forth. And this is the neural network that we're going to design in the workshop. Next, we're going to use the handwritten digit data set to train it from scratch, and then we're going to test it on a few handwritten digits of our own and see how it performs. Before we do that, I would like to illustrate a little bit more how the convolutions and pooling work. So there's this great site that there is a link at the bottom of the slide. You can go there and it actually implements LeNet-5 network in the browser. So you can draw different digits and see what the different layers do with those digits. Here I just took one example and captured the intermediate outputs. So the first convolution that the neural network came up with looked something like this. The second output of the different convolution was this one. So we can kind of see that the neural network is trying to figure out different types of edges, horizontal, vertical, sideways, and so on. Then once we're done with convolutions, we go to pooling, and all that pooling does, it basically shrinks the image. So you can see that it kind of makes sense, right? Same image, only smaller, more compact. So now we do pooling. Pooling just shrinks the image, really doesn't do anything else. And then we'll go to the next convolution that is now based off of these smaller images. And as we go further down, this becomes a lot less intuitive. All these convolutions and outputs do help the neural network to achieve the result, but now we can't really understand what it does exactly. So in this continues, so now we're hitting this fully connected layer where basically we have a flat array of neurons. So this is 120 of them, that's 84 of them, and finally the last layer connects to the last layer has only 10 cells, and the cell that corresponds to the input number, if the prediction is correct, will fire. So in this case it would be 0, 1, 2, 3, and the number is 3, so the network made the correct prediction. So that's how the input number propagates to the neural network to achieve the final prediction. So in the next section, we're going to take these ideas, look at the design of the neural network called LeNet-5, and we're going to use PyTorch to implement the neural network and run it in production and try our own handwritten numbers and see how we do.